Hello, in this video we are continuing our discussion of section 8.4, specifically now talking about the ratio test, and we're going to apply it in example 6 to test this series, the sum from n equals 1 to infinity of negative 1 to the n times n squared all over 4 to the n for absolute convergence. So the one thing that I want to point out here before we start the solution is that remember, the ratio test can be used to test for absolute convergence. It can also be used to test for convergence, but we can get a result saying that a series absolutely converges or diverges if we apply the ratio test. So, in this case, I'm going to work through the same steps that I did in the previous example. I'm just not going to split them up quite as much as what we saw in that solution. So first I am going to set up and simplify my ratio, the absolute value of a sub n plus 1 over a sub n, and that is equal to negative 1 to the n plus 1, n squared, n plus 1 squared, all over 4 to the n plus 1, and then all of that over the a sub nth term, so that's a negative 1 to the n squared, all over 4n. So first off, dealing with this absolute value, n plus 1 squared is positive, 4 to the n plus 1 is positive, n squared is positive, 4 to the n is positive. So the only things that possibly could be negative here are these negative 1 to the n plus 1, negative 1 to the n terms. So if we apply this absolute value here, we can simply take away our negative terms and everything else will be left as it is. So if you want to think about doing something like this, just to take note of the fact that those will cancel out there. Then I'm going to simplify this by multiplying by the reciprocal of the denominator, and I'm going to rearrange the order a little too, so I'm going to pair up the n plus 1 squared and the n squared. So I have an n plus 1 squared in the numerator and an n squared in the denominator, and I'm going to pair up these powers of 4. 4 to the n will end up being in the numerator. 4 to the n plus 1 will end up being in the denominator. Now, for this second term, where we have our powers of 4, notice that the denominator can be written as 4 to the n times 4. So then the 4 to the n's cancel. We're just left with a 1 in the numerator and a 4 in the denominator. For the other term, nothing cancels out there, but you can square out the numerator so that you end up getting an n squared plus 2n plus 1 all over. We're going to have a 4 and an n squared, so we get 4n squared in the denominator. So this is setting up and simplifying the ratio. Then we need to look at the limit as n goes to infinity of a sub n plus 1 over a sub n. This will be, if we substitute in our simplified form, the limit as n goes to infinity of n squared plus 2n plus 1 over 4n squared. To evaluate this limit, we'll multiply by 1 over n squared in both the numerator and the denominator. So then we end up with a limit as n goes to infinity of n squared divided by n squared is just 1. 2n divided by n squared is going to be a 2 over n, and a 1 times 1 over n squared is going to be 1 over n squared, and the denominator we will just get a 4 there. Notice we could have also split up our fraction to simplify this, n squared over n squared, n over n squared, 1 over n squared, and we end up with something similar here. If we wanted to simplify it a little more, dividing everything through by the 4, we're going to get a 1/4 plus 1 over 2n plus 1 over 4n squared. And now if we evaluate that limit as n goes to infinity, this term goes to 0, and this term goes to 0 as well, and all we are left with is a 1/4. Now the last thing that we have to do for the ratio test is to come to a conclusion. This 1/4 is less than 1, so according to the ratio test, that means that this converges. So the series converges, and in fact it's going to converge absolutely by the ratio test. And therefore, we are done with this example.